So good morning, everyone. What I'm going to do now is I'm going to talk about WKB approximation, which is a method that allows us to describe processes such as tunneling and propagation of wave functions in smooth potentials of arbitrary shape. So our key motivation here is to look at potentials that are actually much more realistic than what we have seen so far. Because so far in your undergraduate course, you have studied tunneling and transmission through a barrier using idealized, meaning step function potentials. But we know they don't occur in nature. So we would like really to treat potentials of arbitrary shapes and describe these problems for potentials of arbitrary shapes. So far, if you're looking at tunneling, if you're looking at transmission, what do? You consider you have a particle of energy E. This problem is typically assumed to be statical, so you can write it and describe this evolution using the time-independent Schrodinger equation. And you assume that Vx is equal to V naught, so that you have some kind of step function. And this is something that you take then in distinct spatial regions. So you're approximating your potential by step functions, and at the end of the day, you are solving an eigenvalue equation because you're going to have H psi, where psi x here is the wave function, written in terms of the x coordinate, equal to E psi. So if you do that, as we are usually used to doing, this is going to give you this expression. So you have here, in general, a wave function, which is characterized by one wave propagating to the right, the other propagating to the left, for the classically allowed region. This means if E, which is the energy of the particle, is bigger than V0, and we know that this P, which is the momentum, is 2m E minus V0 square root, right? This is something we have learned before. And we also know that if the energy of the particle is smaller than the energy of the potential, you will have solutions that are exponentially increasing and exponentially decaying, where Q is given by this expression. These are solutions you can find analytically. These are analytical solutions. Now, what do we do to find the full wave function? We apply boundary conditions, right? You have one region, for instance, where you are dealing with dynamics that is classically forbidden. You have a region in which you're dealing with dynamics that are classically allowed. So what you do is you apply boundary conditions at the boundary between such regions, and you have to connect the solutions somehow, right? And here, emphasis on this word, connecting. And it's very important that across this boundary, the first derivative of the wave function and the wave function must be continuous. So what we are doing is we are representing the wave function across the space, and we want to describe a certain physics. And there are regions which we need to take into consideration, and that the solutions are going to behave differently depending on the region. So because it's just one wave function, it has to be continuous. So those are the impositions that we make. We say the wave function and its first derivative must be continuous across this boundary. For instance, if you have this, right? We have here a potential step of height V naught. So this is potential plotted as a super function of x, the x coordinate. Here you have a particle whose energy is E. In this region and this region, E is larger than V naught, but here in region 2, E is smaller than V naught. And when E is equal to V naught, which happens here and here, in points A and B, we have what we call classical turning points, because these points would correspond to points in which the speed of a classical particle would slow to 0. So the problem that we have is we would like to solve this more realistically, as previously stated, and we know that constant potentials or step functions, they are poor approximations to what is really going on in nature. So that's why we need the WKB approximation, and this is going to allow us to solve the time-independent Schrodinger equation for a potential Vx varying sufficiently slowly. And this is applicable to problems that are 1D or reducible to 1D. For instance, sometimes you have a symmetry of a problem. If you're dealing with tunneling in a linearly polarized field, for instance, you can do some transformations and apply some tricks and reduce it effectively to 1D. Then you can also apply this type of study. And if you have constant potentials, what we normally have, we have this momentum, which is P square root of 2m energy of the particle minus the potential. And we have a fixed de Broglie wavelength, lambda, associated with the particle, which is the Planck constant divided by the momentum, right? Let's assume now that this potential varies slowly with regard to the Broglie wavelength. So if we make this assumption, what are we going to find? We can write this similarly. If the potential varies totally crazily, then you get into trouble with this type of assumption. But if it varies slowly, you can write a px, which is a generalization of what you had here on the left-hand side. So it's square root of 2m e minus vx. And you can also define a de Broglie wavelength, which is h divided by px. So effectively what you're doing is you're generalizing what you had here. And this is a very important assumption. It has to vary slowly with regard to lambda x, or even lambda, with lambda x, because lambda is going to be constant in this region. Okay? So the WKB wave function, we then assume that it has a similar form to that wave function in the idealized Vx equal constant case. So where you had here IP divided by h bar, we consider multiplied by t, we consider here Sx, whereby it's a similar form. We're going to come up and we're going to discuss what this is. Okay, so this next step is going to be done in a whiteboard style, because it's quite technical and it's important that you get it. It is also new, a new topic for all of you.